Hello everyone, my name is Grigorios Kostopoulos, representing the National and Kapodistrian University of Athens. My presentation today is titled For the Printing of Complex ABS Structures, Experiments and Thermomechanical Modeling of Shape Morphing Beams. While much of the current research focuses on PLA, in this study we explore the potential of ABS. We aim to prove that with the right printing strategy and valid numerical models, standard ABS can be used to create complex active morphing structures. Let's start with the motivation. 4D printing allows us to create programmable structures that change shape over time. This is ideal for soft actuators and deployable systems. However, fused deposition modeling with ABS is often treated purely as a method for making static, rigid parts. We identified a gap in the field that there is a need for simple design rules and, crucially, validating finite element models that can predict how ABS will morph under thermal activation. Therefore, our objectives were threefold: to first to demonstrate thermally activated bending and torsion in ABS beams, second to reproduce these behaviors using finite element simulations, and finally to combine these simple beams into more complex self-folding structures. To achieve this, we utilized standard ABS filament printed on a Creality K1C printer. The fundamental building block for our study is a simple beam, 60 millimeter long, 6 millimeter wide, and 1.6 millimeter thick. The key behind the 4D effect lies in the printing strategy, specifically the asymmetric layout. We printed 10 layers total, but we changed the raster angle, that is the print direction, through the thickness. To achieve bending after heating, we printed 6 layers at 90 degrees, followed by 4 layers at 0 degrees. To achieve torsion after heating, we printed 6 layers at 45 degrees raster angle and 4 layers at minus 45 degrees raster angle, as we can see in these figures here. This opposing diagonal pattern induces a twisting motion when the beam gets heated. Our activation cycle is purely thermal. We use a thermal chamber heated to 150 degrees Celsius. We place the specimens inside this thermal chamber for 15 minutes. The process shown in this diagram involves three states. First, we have the as printed part, which is flat but contains stored elastic energy from the printing process. Then this beam is placed inside the thermal chamber and it gets heated. As it reaches 150 degrees Celsius, the polymer chains relax and the stored stresses are released, causing the deformation. And finally, we place the bent beam outside the thermal chamber to cool down in order to lock the new permanent shape. A key part of this work is the ability to predict this movement. We developed a coupled numerical model using ANSYS workbench. This was a two-step simulation. We first applied the 3D temperature field to simulate the heating in the chamber, and we then imported that temperature field into a structural analysis with large deformation enabled. Crucially, to accurately capture the material behavior, we modeled the beam as a layered composite. for the material properties, we did not rely on generic isotropic values. Instead, we assigned specific orthotropic coefficients of thermal expansion and a temperature-dependent elastic modulus derived from the experimental work of Good et al. This rigorous material definition allowed us to correctly simulate the internal conflict between the layers that drives the morphing. Let's look at the results now, starting with the bending mode. Here we used the 90 degrees raster angle layup. The mismatch in thermal expansion through the thickness drives the beam to curve into a ring, what we call the ring closer mode. As you can see in this photo, the physical beam closes into a near complete ring after 15 minutes at 150 degrees Celsius. And the finite element model shown in color here successfully predicts this final curvature. Next, we investigated the torsion mode by changing the layup to 45 and minus 45 degrees raster angle. We introduce shear stresses that result in twisting motion. Again, in the experiment, the red ABS beam exhibits a clear uniform twist along its length, and the numerical model captures this complex 3D deformation with good qualitative agreement. This validates that our layered modeling approach works for both simple bending and complex torsion. Finally, to prove that these aren't just academic curiosities, we upscaled the concept. We designed the complex structures composed of multiple morphing beams. For example, we can see a star-shaped assembly that, upon activation, the arms bend upwards and interlock. Secondly, on the bottom, you see that the flat flower pattern, and upon hitting the petals, bend upwards. These demonstrators prove that we can program complex multi-axis shape changes into a single flat print. In conclusion, this study confirms that ABS is a viable candidate for 4D printing applications. We successfully induced controlled bending and torsion using asymmetric layups. Crucially, we validating a transient thermal structural finite element model that accurately predicts these shapes. We demonstrated the scalability of this method with complex assemblies like the self-folding flower. For future work, we plan to extend the finite element model to simulate these full assemblies and move toward inverse design, where we define the target shape and the algorithm tells us the necessary printing path. Thank you very much for your attention.